Hello again, I'm Yu. This presentation is the second part of the introduction to photometry of LED lightings. In the previous presentation, standards for LED lightings were reviewed to be categorized into optical parameters of photometry, electrical parameters, and reliability tests and luminous flux maintenance. In this presentation, photometry of LED lightings will be explained as the introduction to photometry of LED lightings, part 2. As I presented, photometry is measuring visible light through the human eye. The optical performance parameters such as luminous intensity in the unit of candela, luminous flux lumen, illuminance in lux were explained in the previous presentation. In this presentation, luminance in the unit of candela per meter square will be explained. As a parameter of radiometry, there is wavelength, there is spectral luminous intensity according to the wavelengths, or spectral illuminance according to the wavelengths. Other parameters of photometry are color coordinates, color temperature or correlated color temperature, color render index, luminous efficacy. Luminance in the unit of candela per meter square is a luminous intensity from a unit area of a large light source or a wide projected surface. Luminance of a large light source, like flat panel display, is measured with a CCD photometer or calorimeter, which is defined by luminous intensity over display area. Another measurement of luminance is luminance of a wide surface projected by a luminaire. If there is a surface like a wall spotted by a luminaire, the luminance of the wall is measured in the same method. Load surface is treated like the wall. Load surface illuminated by load lightings is also like a projected surface. Therefore, luminance of load surface is measured as the same way. The photometer is located more than 6 meters from the load surface to be measured. This slide shows examples of luminance measurement of display or LED modules. In the actual measurement of a flat panel display, there are two kinds of measurement. One is moving CCD camera and measuring 9 points. The other is fixing the CCD camera and measuring 9 points. The below photos are measuring luminous intensity distribution of LED packages or LED packages. To measure wavelengths, there is spectral luminous intensity. Spectral radiometer will be used. Spectral radiometer is composed of mirrors, grating mirrors, and detectors. If a white light source passes through a prism, or reflected by a grating mirror. The light will be spread depending on wavelengths, like rainbow, where you can see red, yellow, green, and blue colors. From this slide, example spectra of light sources will be shown. At the left side, the spectrum of a fluorescent lamp of 3 wavelengths is shown. At the right, the location of fluorescent lamp, the symbol of red star, is shown on the CIE 1931 chromaticity diagram. That is the CIE 1931 XY color coordinates. The symbol is very close to orange. As references, the red color is located here, and the green is located here, and blue is located here. And around here, there is yellow color. This is a red LED spectrum peaked at 660 nanometer. And the location on the CIE color coordinate is here. This is a yellow LED spectrum peaked at 569 nanometer, and the location on the CIE 1931 chromaticity diagram is here. This is green LED spectrum peaked at 525 nanometer, and the location on the CIE chromaticity diagram is around here. This is a blue LED spectrum peaked around 450 nanometer, and the location on the CIE 1931 chromaticity diagram is here. The center graph shows spectral distribution of various LED samples. The dotted line in the left here is the spectrum of an LED package with blue LED and phosphor. The center green dotted line here is V lambda, the luminous efficiency function of human eye, and later it will be Y bar lambda. The broad yellow line here is the spectrum of phosphor. From the spectra, you can directly derive optical characteristics such as peak wavelengths, full width at half maximum, that is bandwidth, center wavelengths, and centroid wavelengths. From a spectrum of a light source, the location of the light source on the CIE 1931 chromaticity diagram, that is CIE 1931 XY color coordinate at the right side, can be derived. From the diagram, XY color coordinate, color temperature, correlated color temperature, that is CST, purity of color, color rendering index, and dominant wavelengths will be derived. This slide shows the calculation of several spectral characteristics of an LED spectrum. Most of them are radiometry. Peak wavelength is the wavelength at the maximum power of LED. Bandwidth is the bandwidth of two wavelengths at the half of the peak power. That is, pulleys at half maximum bandwidth. Center wavelength is the arithmetic mean of the two wavelengths, like this. Centroid wavelength is the weighted mean of the spectrum of the LED, like this. Dominant wavelengths will be explained later. From this slide, most parameters of photometry are derived from a chromaticity diagram, that is, color coordinates. Chromaticity diagram can be derived with tri-stimulus values of x, y, z. The values are multiplicative of LED spectra, D illuminant spectra, and three spectra of standard observer, X bar, Y bar, and Z bar. From the three stimulus values X, Y, Z, XY, UV, or U prime V prime chromaticity diagram are calculated. In the colorimeter method, three color filters simulating standard observer X bar, Y bar, and Z bar are used to measure the spectral curve of LED, like this. To the contrary, spectroradiometer is used to measure the spectrum. For binning LEDs, colorimeter method is inadequate. Therefore, spectroradiometer method is recommended for the binning. This slide represents how to calculate the three stimulus values, large X, large Y, large Z, and then small xy, uv, or u prime, v prime coordinates after measuring LED spectrum using spectroradiometer. One of those three stimulus value, large X, is integrating I lambda times x bar lambda by wavelengths, and then multiplied by K. That is 683 lumen per watt. Large Y and large Z are calculated as the same procedure. Small xy color coordinates can be calculated using these formulas. UV color coordinates, that is CIE 1960 chromaticity diagram, can be calculated using these formula. U prime V prime color coordinates, that is CIE 1976 chromaticity diagram, can be calculated using these formulas. U prime V prime color coordinates has equal space in the coordinates, therefore displacing unequal color space of xy color coordinates. Color temperature is extracted from the location on the color coordinates. At first, black body at a certain temperature radiates light with a spectrum corresponding to the temperature. That is Planck's law. At second, the spectrum gives three stimulus values, large X, Y, Z, and then they give a point located on the chromaticity diagram. And if the black body temperature varies, the radiative spectrum changes, and then the point on the chromatic diagram shifts to give a line like this here. That is called the blackbody locus or the Planckian locus. Color temperature will be determined by the spectrum of light on the blackbody locus. Correlated color temperature, that is CT, is a light, is the closest CT of the blackbody. This slide shows the spectral variations according to the blackbody temperatures. The higher the temperature of a blackbody, the more the blue light is generated. The blackbody of 3000 Kelvin gives a spectrum of the rose line. Around here, incandescent lamp and halogen lamp are located. The blackbody of 6000 Kelvin gives the middle line, and the color is the same color of the clear sky, like this. This slide shows the colors of the color temperature and the corresponding colors of LED lightings. This slide shows the nominal CSTs with A grades, which are defined in NC 378.377A specification. This slide compares the 7 McAdam ellipses of compact fluorescent lamp and the ranges of nominal CSTs. The numbers of McAdam ellipses are 7 here, and the nominal CSTs are 8. Color rendering index, CRI, is a parameter indicating how a light source makes the color of an object appear to human eyes. Color differences of the 14 color test samples by comparing the reference source or blackbody with the light source. The maximum value of CRI is 100. The left color spectra are the spectra of the reflected light from the test color samples, TCSs. At the right table here is the name of TCS samples, the approximated Munchel color, and the appearance on the daylight. This slide shows the effect of different CRI values. The higher the CRI values, the clearer the colors under the light sources. This slide shows the effect of CCTs affecting or controlling emotion of users. The left is the CCT of warm white, and the right is the cool white. CRI is not good parameters for LED lightings. The low saturation of TCS color samples result in low score for saturated light. In the right graph, the CRE LAB cut A delta shows red and green. B delta shows yellow and blue. So red, yellow, green, blue. The higher the number, the clearer the TCS colors. Here, red is dominant. Even though the CRI values of the test light is lower, the appearance of the TCS colors is clearer than under the reference sources. Therefore, CRI can penalize light sources having enhanced light contrast. So they want to change CRI values to another references. In this slide, dominant wavelengths and color purity can be determined in the CIE 1931 XY color coordinates. This point is neutral white point W, and this is a point of light source. Then connect W and C and extend it to the envelope of the color coordinates. The wavelength of the crossed point on the envelope here is the dominant wavelength. Color purity can be determined by these formulas. With the XY values of neutral white, XN, YN here, and dominant wavelength coordinates XD and YD here, and X and Y is the XY coordinate of light source. Luminous efficacy is in the unit of lumen per watt. LED efficacy is not constant. As current and junction temperature increase, the efficacy decreases. Then LED efficacy determined by luminous flux over electrical power. And system efficacy is not the same as LED efficacy. System efficacy in lumen per watt is determined by LED efficacy times electric efficiency in percent times optical efficiency in percent. In the next presentation, electrical parameters and reliability tests will be explained. Thank you for listening. Have a nice time.